if you can enter, can you draw a converter? No. But the other problem is, can you enter a DC voltage gain you want and get the new converter topology? And you know what's surprising? You know, that two converter had an input inductor, output inductor, one capacitor in the middle, and switches which came in a pairs. 2 switches, 4 switches, 6, and so on. But that particular one had only 2 switches. Now you set up the problem and say, how can we make any connection? First of all, let's see how many connections there are. I think you will be surprised. 1 million possibilities. Dr. Maximovich, who is now full professor at Boulder, Colorado, and my first PhD student, Bob Erickson, is also the chairman of the department for many years, and they have their own student who is also now in digital control as a third professor, so they have a pretty strong program in power electronics. He made up this program basically using a single criteria. That was that state space averaging equation, which says if it has a solution, it is converted. If it doesn't, it's not converted. And in out of the million possibilities, some of them are low-pass filtered, some are high-pass filter, but only few of them had a steady state and DC output. And there are only about 30. Well, I was really glad because the Chu converter came out one of those because I invented it before that computer program, okay? So that was nice. And this is what it does. Graph theory, a lot of the math, a lot of fancy circuit theory and so on. And then eventually, when you come down, you realize it, and this converter ends up being called 243,146.2. You know why? Because it's a different orientation of branches, different current through it, and so on. Branch orientation and position and so on, okay? And it's only, we're talking here. Remember, we're talking here only 2 inductors, 1 capacitor, and switches in pairs. We're not talking even about isolation transformer in it. We're not talking even about more switches or more inductances and so on. Just this. So now, that was in 1988, there was a cover page on, that's where things started going wrong, in my opinion. You know, both universities and industry succumbed to one thing and one thing only. They didn't know how to improve further. Reduce the size and increase efficiency, but mainly reduce the size. And the only way was available is just go, increase switching frequency unbounded at the cost of reducing the efficiency because of losses of devices, etc. So people are talking, oh, we go to 10 megahertz now, and we don't have to have magnetic cores. We can only do a wire, like air core inductors or air core transformers. Of course, that was pretty, dead end because pretty soon they realized they couldn't do that. Although that still goes on. And I gave a paper at the San Diego conference in 1988, and before that it was a cover on Power Techniques magazine and so on. And at that time, we were talking about efficiency of 83% being record efficiency cool and high power density of this level. Now, I think I'm glad to say a lot more can be done and much better now, and that is where the challenge is. Because now, when you have efficiencies to 98%, and we know when the system is 99.9% efficient, it is difficult to control. You have no cues. All the filters are all over the place. So you have to have a very, very strong control. Digital control is here. We can do that, and many other things. So it was 1998 class, 1 year before my leaving Caltech. Last class that year, and Caltech students are known for their pranks. So this is what they did. You see, I came that day to my last class, and 2 o'clock in the 11 o'clock in the morning or 10 o'clock in the morning, and I come. It's new auditorium, which is like a slanted, like a beautiful auditorium, Moore building, and I come in it, and it's dark, and I says, they come earlier, 1 hour, so nobody's in the class, and then I notice one kid there looks at me and says, Professor Chuk, take off your shoes, and I see all their shoes are off at the entrance, and then I listen, there is the Orthodox music playing, So what they did, they knew of my infatuation and, what I told them, and make some lecture in my basic course on W40 fundamentals of energy processing on Tesla. So they somehow made a big printout from my 3-volume book on the back. Here they found this picture of Tesla inside. I think it's here. So they copied it and made it into the big printout. They put a they put a big candles here and smaller candles, and right in the front of it you see kneel here. So, so what I did, I had to take off my shoes, come in front and kneel and so on. And of course, after that, my class was not anything. That 1 hour class was, I called my assistant. They brought my demonstration of Tesla inventions, rotating magnetic field, Columbus eggs, etc. And then after that, I dismissed them for the other 2 classes. So at least they got 2 free classes that day. Of course, everybody got a good grade. So I don't think anybody got anything less than A minus, but you know, I felt good about it. All right. So in '99 till now, then I moved at that point for one reason or another. You know, we are at the university. University decided with that they are moving into the communications. You know, their departments grew up, 5 more professors, etc. So I ended up saying, okay, I'm moving to my company and do my basic research there. I had some of my former PhD students join me there, and I did from that time till now a number of things which are listed here. And I want to give you just impression of why this field is so live and well. And here is basically the standard wave full bridge converter, which is extension of the buck converter. Again, notice here, transformer, and from basic converter, which is just inductor and capacitor on the output, to put isolation transformer, you need 8 switches because you're not using capacitance of any capactor. Now, and 3 switches are forbidden. In all this theory that we had is inductor and capacitor transfer energy in, how you say, very complementary ways. So you need 2 switches, 4, 6, or 8. So therefore, we never looked at the possibility. That's why the total area of 3 switches are missed. That's what I call hybrid switching. So now, when you have hybrid switching, resonant capacitor, resonant inductor, you enter, there is a new switching method. Suddenly you have a large number of converter configuration you can generate. And what you can do with it? You can do many things that you couldn't do before with a regular, for example, AC to DC conversion. What's the problem? A regular AC to DC conversion, now I say regular, standard, which is used in industry and everywhere, they process the power 3 times. Because here you have a full bridge, you have the rectified AC line, then you have boost converter operated as a power factor correction, making current in phase with the voltage and proportional, and then you get 400 volts DC, then you have isolated converter with 8 switches, and you have energy storage here. So you have total of 14 switches. Do we need to do that? Well, turns out we don't.